Now let's dig into where and when the Cottrell equation breaks. Basically, what non-ideal behaviors are manifested in actual experiments which cause the current response to deviate from the Cottrell equation. First and foremost, resistance. Resistance basically drops your potential. This is often called ohmic drop because according to Ohm's law, the resistance within a circuit or your electrochemical cell, which is a part of the circuit, drops according to I times R. So here we have our current times by our uncompensated resistance. Your potentiostat or your power supply may be outputting a square potential step, but in reality, the applied potential at your electrode is not a square potential step, because at the beginning of our measurement, we have this huge current spike, which then results in a huge ohmic drop, especially at the short times. This results in a distortion, as you can see here on the right. The square potential step is represented by the light blue dashed line, and then the distorted potential that's actually being applied at the electrode due to resistance is in that dark blue. Most modern potentiostats can actively compensate for resistance, and what that does is you measure the resistance, you tell the potentiostat the resistance value, and then times whatever current it reads by that resistance so it can add it back in to the output to compensate for the drop. Now, because this is done in a positive feedback loop, if you approach 100% compensation in most systems, you will get oscillation and ringing. Typically, you can only compensate 85, maybe up to 90% of the resistance. If you really need highly accurate, you are going to need to account for the uncompensated resistance using simulation after your measurement. The next thing that can distort our current response is double layer charging. And we learned about this in the overview, lesson 1. It has this exponential decay function, and how long it's significant is determined by what's called the RC time constant. That's our solution resistance and our double layer capacitance. The resistance is related to the electrode spacing. The wider my spacing between electrodes, the higher my resistance. The resistance is also related to surface area. The more surface area I have, the lower my resistance. However, double layer charging is also related to surface area. And the higher my surface area, the higher my capacitance is at that electrode-electrolyte interface. This table here on the right shows how your RC time constant changes in milliseconds as your electrode spacing and your surface area changes. As you get to high surface area electrodes with wider electrode spacing, you get higher RC time constants. What does this look like? I'm going to sketch for you what this looks like. Don't get your hopes up. I'm not a great artist. The double layer response has this exponential decay, and I'm doing a dotted line to show that. The diffusion controlled response of the Cottrell equation has a 1 over the square root of t response. So something like this. It decays more gradually, but short times, the double layer charging is significant. And at longer times, the diffusion controlled current response becomes dominant. Nucleation effects are another factor to consider if you have an insoluble product. Maybe you're depositing a metal out onto your electrode. And that manifests as these humps that show up in your curve. So basically your current's decaying and then spikes back up and decays back down as you nucleate and form these new phases on the electrode. Now, there's a lot of relationships out there. There's a whole field that studies these nucleation effects. Right now, I'm just trying to get you familiar with these. You can see how nucleation effects deviate from the Cottrell equation. For example, here with copper deposition onto platinum, we can see that we have the Cottrell equation plotted here. And we can see how the nucleation of the copper onto the platinum phase creates these curves that are quite different from the Cottrell equation expression. However, at longer times, beyond a second, maybe even 2 seconds, we start to converge and come closer to the Cottrell equation. And all of this is to mainly make the point that if you're trying to be really accurate in calculating diffusion coefficient or concentration from the Cottrell equation, you need to be very cautious about applying it to something with an insoluble product, because nucleation effects could be causing significant deviation at certain times. Issues at long time scales include surface area growth. Again, if you're depositing a metal or some other insoluble product, that could be growing and changing your surface area. Natural convection can also cause you to deviate from the Cottrell equation, especially at long measurement times when that current has really decayed low, and now you could have some natural convection enhancing the mass transfer to the electrode. And that would look something like this plot here, where you have the Cottrell equation, but you can see as we approach a second, it no longer decays, it actually grows out, and that could be due to natural convection or surface area growth. In my experience, natural convection is most likely the culprit here. Surface area growth looks more erratic, and the current line looks more like this. As the area grows, maybe dendrites form and fall off, you get a lot more noise in that current response. Another issue at long timescales is radial diffusion. Often in molten salts, we use a cylindrical electrode, like a wire or a rod, and at short times, our diffusion layer is thick and most of the flux is perpendicular to the electrode. However, at longer times, you can see if I am diffusing from further out, I could be getting flux from a couple different angles as it narrows down and gets closer. This is what's called radial diffusion. Rather than just having semi-infinite linear diffusion, which is like this, I actually have a couple flux lines converging to my surface, creating a lot of more flux than I would than semi-infinite linear diffusion. All right, that's a quick survey of the ways that your chronoamperometry experiments could go wrong. I'm sure there could be more. Next, I'll be covering a diagnostic tool for you to gauge when you may actually be following the behavior expected in the Cottrell equation. This will help you know when these issues that we've just discussed are actually significant and when they may not be.